Okay, here, a closed bottle of a carbonated drink. Okay, so if here's your soda, let's make this Coca-Cola. So, what's the shape of a Coke bottle? Like that. All right. They don't come in those bottles anymore, huh? All right. So the 4 atmospheres of CO2 here, CO2 gas, and you've got CO2 in your soda. What happens if the bottle is open? Here's the equilibrium. There's an equilibrium between CO2 in the gas phase and CO2 in the aqueous solution. And then you open it up. What happens when you open it up? The equilibrium shifts to the left or to the right? Or does it have no effect? When you're opening it, what are you doing? What's the pressure outside the bottle? How much CO2 is in the air around you? You have 1 atmosphere of air around you, but how much of that is CO2? Very low, right? It's about 20% oxygen, almost 80% nitrogen. You have trace amounts, strictly speaking, you have very, very small amount of CO2 in the air. So you lower the amount of CO2 in the air that's above, in the gas that's above your soda, your liquid. So what happens? If you lower the pressure, what will it try to do? You lower the amount of CO2 in the gas, what will your system try to do? What's the opposite of removing CO2 gas? So the net effect of opening the bottle is to remove CO2 gas. So which way will the reaction shift? Shifts to the left, right? You're removing CO2 gas, so you shift to the left. And what's the physical manifestation of that shift to the left? CO2 from the liquid is going to bubble out of your soda. Okay, so that's what happens. Okay, now we've talked about this earlier. Okay, basically what we said was that the solubility of a gas in a liquid is directly proportional to its partial pressure in the gas that's in equilibrium with that liquid. That was Henry's law. Okay, so the concentration of A, if A is a gas, okay, concentration of A in the liquid that's dissolved in a liquid is directly proportional to the partial pressure of that in the gas, and that ratio of those two is what we call the Henry's law constant. So you can see this ratio, concentration of A in the liquid over partial pressure in the gas, that's really the equilibrium constant for this. Okay, so Henry's law constant is really nothing more than just another equilibrium constant. Okay. Here's another example. You have a closed container. Liquid water is in equilibrium with water vapor. So I've got liquid water here, and I have water vapor gas there. So you got equilibrium. What happens if I add sodium chloride to my water? Vapor pressure is, remember your colligative properties? What's the answer to this one? You add a non-volatile solute to a liquid, what happens to the vapor pressure of the liquid? It's lowered, right? Raoult's law. P of water is going to be P star water times the mole fraction of water, right? So it's lowered. The vapor pressure is lowered. Okay. How is that illustrating Le Chatelier's principle? By putting sodium chloride in your water, what are you doing to the concentration of water, to the activity of the water? Okay. Your reaction quotient is partial pressure of the water vapor, okay, this is gas, over the mole fraction of water. So if you're contaminating your liquid, you're lowering the mole fraction of your water in the liquid, what happens to Q? It goes up. And so if Q goes up, which way will the reaction shift? If Q increases, right, mole fraction of water goes down, Q increases, which way will the reaction shift? Momentarily now you've made Q bigger than KEQ, so the reaction shifts to the left to make Q smaller again. So shifts from gas to liquid. That's why your vapor pressure of water is lowered. So that's one way of looking at Raoult's law. Okay? So in fact, if you look at right here, here's Raoult's law, right? P sub A is P sub A star times a small fraction of A. If you divide both sides by XA, you can see that P sub A star is really nothing more than just another equilibrium constant. Okay? So you can think of Raoult's law in terms of a reaction where you think of it as like a reaction, as if it's a reaction where you have liquid water as your reactant and gaseous water as your product.